So, any questions about the last class, about spectral theorem? Okay, we proved a spectral following theorem. We proved if T is a normal operator, then corresponding to this T, there exists a spectral measure. There exists a P from the Borel sigma algebra of complex numbers to B of H on H. We have a normal operator and B of in B of H. Then there exists a projection valued measure, spectral measure. This is what is called spectral measure. There exists a measure. There exists a function P from Borel sigma algebra of complex numbers to B of H, such that P of E is a projection. And P is countably additive. I mean, it's the same definition which you have for complex measure or finite measure. It's the same definition. Countably additive. If you want, you can further say that P of E is 0 and P of C equal to 1. Okay. I mean, in fact, P of the spectrum itself, indeed, P of sigma of T equal to 1. And then it further satisfies the condition further. This function Pxx of any E equal to P of E xx. Okay. Then for any given x in H, we can consider this function, okay, for E and BC is a positive, finite positive measure. It's a measure. And that's just clear. It follows from the sigma additivity and all that. And for all xy in H, this E going to Pxy equal to P of E xy, okay, is a complex measure. So we proved all that, satisfying the following. It's a complex measure, it's satisfying. So you can, if you have a complex measure, you can integrate with respect to the complex measure. And you can integrate this function, f of z, dp xyz, okay, over C. This is equal to, but then for any normal operator T, we have the function f of t. So f of t xy for all f in L infinity. I mean, we have a L infinity mu. I mean, or you can say, you can forget about L infinity if you want for all. I mean, if you are worried about mu, there is a mu. You can always define this for any bounded measurable function. Okay, in particular for bounded. So there you don't need to worry about the measure. Bounded measurable function. Measurability just depends on the sigma algebra, and boundedness you can always define for a function. So for any bounded function, this is well defined. Further, it says from this it's clear that the measure is unique from this property star. Star implies P is unique. I don't know, in the book it says something satisfies all these properties is unique, and then he gives a proof using Stoneway-Strass theorem. I don't really understand why that is needed, because if we have two measures, indeed, if P and P prime are two measures satisfying those conditions, two spectral measures, then we have, this is a bounded function, okay, 1e of t, 1e of t, 1e is a function, 1e of txy equal to that integral over e of pxy, which is equal to p of e. And this is also equal to, by the same reason, which is also equal to p prime of e. So p of e and xy of e. Okay. So this implies that p prime p of e xy equal to p prime e xy. So this implies p of e equal to p prime e. Okay, because for all e. So by the definition, it's clear, but I don't need why that is needed. But I think the following is true, which I give it as an assignment. I'm very sure. I mean, I know it's true, but I didn't really verify now to see the proof. But I give it as an assignment. So I'm sure it is true, but I want you to try this. Okay, assignment. So show the spectral measure is unique, but you don't assume this condition. You assume only the integral for the lambda. So show a spectral measure. By spectral measure, I mean a projection valued measure. Okay, maybe I will write that. Show a projection valued measure satisfying. So let T be a normal operator. Let T be normal. Okay. Then a projection valued measure satisfying this equation. This T xy equal to integral over z dp z. dp xy. Okay, where pxy denotes the same thing. Is unique. So suppose if we have two spectral measures satisfying this equation, I am not assuming for f. With f, I don't see anything new about it. But just with z, you can prove it. Okay, so that's what I want you to do as an assignment. This is assignment 1. Then the assignment 2 is, that's you can look at Sundar's book for a hint if you want. The proof is consider the operator for so T be normal for f in L infinity mu whatever, or you can assume f bounded measure. That's also fine for me. Okay, compute the spectral measure. Find the spectral measure. Compute the. This is a good exercise for f of t. Okay, you know the spectral measure for t, which is the p. So what is the spectral measure for f of t? Okay, so that's what I want to do. So these are the two assignments. Okay, so fine. So now let us consider what is this mu. We were talking about some, using, when you have the spectral measure, you can write the mu. That's what I want to try. So this is the remark or observation, maybe proposition. Let us call this proposition. T normal P1. Sometime you may be able to find the spectral measure. You don't need to go through those mu and find that. Then you will know, you will find a candidate for mu. The mu is unique up to absolutely continuous. You can change the mu by any measure which is absolutely continuous. Then the L infinity will not change. The L infinity is going to remain changed. The mu is the measure. For any given normal operator T, there is a background. We have a L infinity which is given by a mu. So that is in the background. There is a mu. That mu comes from the C of x. Okay, it comes from the continuous function, the representation of that, and it's through some complicated procedure we got it. That's an abstract mu. Okay, so for T normal, P the spectral measure of T then the following are equal. 1. So we want to find the mu up to mutually absolute continuity, up to that equivalence. Okay? So because it is unique up to that. Okay? So P of E equals 0 for all E. See, which is equivalent to 1E equals 0 for all these. And the third one is mu of E equals 0. These are all trivial. It's all clear. Okay? The fourth one is what we want to do, which is Pxx equals 0 for your total set. Total subset of H. Total subset means you take the span and then the closure. That should be the whole of H. Okay. So the proof, I think mostly it's clear. So P of E equals 0, 1E equals 0 is clear because it's an isometric isomorphism. The 1E going to P of E is the isometric isomorphism. That's what P of E is nothing but 1E of T, okay, by our definition. Okay, so those two are same. And 1E equals 0 equivalent to mu of E equals 0 is just the definition of the measure. 1E is 0 means mu of E is 0. Okay, it's as an element of L infinity is 0, that is equivalent to saying mu of E is 0. So now we prove this 1 is equivalent to 4. Okay, so if P of E equals 0, okay, then certainly P of E, this implies of course P of E x-axis is also 0. But on the other hand, if P of E xx equals 0, this is equal to, because it's a projection, this is equal to saying P of E of norm x square. You can take the P of E, you can write P of E as P of E square, and then you can take a P of E on the other side, and this is equal to norm P of x, P of E x square. This is equal to 0. But if a linear operator vanishes on a total set, then it is 0. Okay. If it vanishes on a total set, then if it vanishes on a set, then it vanishes on the linear span of that, of course. Then it vanishes on the closure because it's continuous. So it is equal to 0. So this proposition says that P of E equals 0 is equivalent to saying Pxx En equal to 0. So in particular, any orthonormal basis is a open set. Any orthonormal basis En is a total set. Okay. So you can take, once you know the spectral measure, then we can take this mu equal to summation 1 by 2 power n P E N E N. Okay. So you can take this as the measure. Then you can consider the L infinity. The reason for knowing this measure is you want to know that is an algebra. This is an algebra generated by all the simple functions and all those things. So it looks like L infinity. So there is an isomorphism between, that is what is called, you take the closure of the strong topology. This is an algebra. So you consider this T and consider the T star and identity. Then you take the algebra generated by this and take the closure in the strong topology. That is what is called the von Neumann algebra generated by that. So you will know the von Neumann algebra. That is exactly isomorphic to the L infinity mu. And you want to know the mu specifically, and that is given by this mu. So the von Neumann algebra generated
like what algebra?
Von Neumann algebra. I will deal with this if I have time. Von Neumann, John von Neumann. This name you must have heard if you do math. You should know if you know mathematics. He has done in many fields, like computer science, about brain, about many things, set theory, logic, and one important contribution is he has done in operator algebras. He invented he is the person who gave the framework for quantum mechanics it's a physics subject, but it's basically mathematics. The framework for, without mathematics, you cannot understand quantum mechanics. You need to, because you want to define all that, you need mathematics. And that mathematical framework is given by von Neumann as an operator algebraic framework. Okay, so you can read his book titled A Framework for Quantum Mechanics or something. That book, it's an old book, you can read. Okay, so, and that is precisely, I mean, whatever he considered, that's what is called von Neumann algebra. I will define this later. We will deal with this later. We already know what is a Banach algebra, C-star algebra. Banach, von Neumann algebra is something, C-star algebra is something which is closed in the norm topology. And von Neumann algebra is something which is closed to the strong topology. And you can actually take in many topologies, strong topology, but you will see that there is a beautiful condition which says that getting the closure in the strong topology is equivalent to, which is a topological statement, which is an analytical statement, which is equivalent to some algebraic statement. I will come to that. Okay, something is equal to its double comitant or something. I will most probably I will have time to prove that. Okay, so I will prove that. So anyway, so this is about the mu, and so any question? Any question? Okay, if you don't have any question, I will just go to next. So next we want to consider, so we have given a normal operator, we can talk about the spectral measure. And for self-adjoint, we initially considered single self-adjoint operator. Then we talked about commuting tuple of self-adjoint operator. And from that only we got the spectral theorem for normal operator. Did I start recording? I think I started recording. Yeah, it's recording. Yeah. So now we want to consider tuple of normal, commuting tuple of normal operators. So we want to get the same theorem, similar theorem for normal operator. To do that, we had earlier proved that if you have one self-adjoint operator, if you have another self-adjoint operator which commutes with that operator, then need not be self-adjoint. Another operator which commutes with that, then that operator commutes with all spectral projections also. Okay? I mean, it in fact commutes with all f of t. If some s commutes with t, then s commutes with f of t. This is for self-adjoint we prove. We want to prove this for normal operator. So this is a particular case of this theorem is what is called Fugledes theorem. So this is the theorem. I want to prove the following: that T be a normal operator, T be normal operator, okay, and S in B of H, and St equal to Ts. S commutes with T, okay. Then what? S commutes with f of t for all f in L infinity, whatever the L infinity. Okay. In particular, S commutes with T star. I mean, this is my notation for commuting. Maybe I'll write it. T star. So if S commutes with T, it commutes with T star, and T star just corresponds to function. T star corresponds to f of z equal to z bar. Just taking the conjugation, which is a continuous function, and it just corresponds to that. Okay. And this statement, S commutes with T, it commutes with, this is what is called Fugledes theorem. But the original proof is different, and this proof is by, I think, by Halmos and Sundar, and there's something, possibly by Sundar himself. This is a, which we have already seen, and we are going to whichever, I mean, this proof is basically a generalization of what we have done for self-adjoint. So we are going to do the same thing here again. Okay? So we want to prove the following. We want to prove S commutes with f of t for all f. So For that, it is enough to prove F commutes with all spectral projection. Okay, because if you in L infinity is generated by simple functions, which are of course linear combination of one E. So since this is just a copy of L infinity is what you have. I mean, f of t, f is any measurable function. So you can approximate this by simple function, and the commutative will follow because I mean convergence will preserve the commutative. And it is actually, I mean, it's actually strong convergence is enough, but simple function will converge uniformly. So when it is a bounded measurable function, simple functions will converge almost everywhere uniformly. Okay? In particular, if it is an L infinity function, it will converge almost everywhere uniformly. No, bounded measurable function will converge everywhere uniformly, but for L infinity, you will have the convergence almost everywhere. Okay, so yeah, so that will give the norm convergence. You can approximate it to norm. So I mean, if something converges with the every element of the sequence, then it converges the limit. Okay. So because of that, it is enough to prove. I don't want to write all that. It's enough to prove for any spectral projections. That's what we want to do. So we want to prove this for any spectral projections. Okay. So for that, we use the following lemma. So let D, maybe D closure equal to this, and D closure is that. D is this, Z equal to mod Z less than equal to 1. Okay, then we take the D closure as the closed disk. Okay. The following are equivalent. We have already proved this for the interval -1, 1 for a self-adjoint and for a self-adjoint operator. Now we want to prove for the disk. Okay. 1. X is in this spectral projection corresponding to this D. T is normal. Okay, we have a normal operator. This is equivalent to saying t power n x norm is less than or equal to norm x for Rn. 3. This set t power n x is bounded. Okay. So we want to prove this lemma, prove our theorem, Fugledes theorem.
This is like similar to Helmholtz lemma, right?
Exactly, same Helmholtz lemma. It is just for normal operator. Instead of that's what I said. Instead of the interval -1, 1, we are taking the closed disk. That's all. We are taking the closed disk in real numbers. Now we are taking the closed disk in the complex numbers. That's all. So we need to, I mean, we are going to prove the same thing for a normal operator. That's all. Okay. Okay. So 1 implies 2 is clear. Why is it clear? That is because so 1 says that x is in the range. I mean, this is range. Okay. I don't want to use that yum notation. You can look at that, but that is unnecessarily confusing, shifting all that. This is in the range of this. Okay. Now x is in the range of 1 d bar t. Okay. Then this implies, okay, let it be. We want to prove the following: 1 d bar of, should we take t star n or this 1 d bar of t. So no, that's not t. As functions, I want to write it as a function. Then I want to translate. I mean, bring it by use the homomorphism to get it as a property of t. You have this function 1 d bar z. Okay. Then you multiply by z. maybe mod z square. This is less than or equal to mod z square. This is less than or equal to mod z square, right? Okay. Maybe not that. I will just write this. Yes. Should I use the function? Yes. Start. Yeah, I can use the mod z square itself. It's okay. Use mod z square. One, this. Mod z square 1 d bar z is less than or equal to mod z square. Okay. Right. So mod z square, I can write it as z bar equal to z bar z. So if I translate this, I mean this identity function f of z going to z is mapped to t. So this becomes t star t 1 d bar of t. Okay. This is less than or equal to, this is just the identity function. I mean this is just no, this is less than or equal to 1. Sorry. These are all positive numbers. I mean, mod z square, 1 d bar z, they are all numbers. So when z is in the disk, its mod is less than or equal to 1. Mod z square is less than or equal to 1. Z is outside because we are hitting it by 1 d bar, it's 0. So this is satisfied. Okay. Let me write it like this. Z bar z into 1 d bar z is 3. So if you apply the mapping pi, or apply the f of f or whatever, the map f, then z bar will go to t star, z and it's a homomorphism. Z bar will go to t star, z will go to t, and 1 d bar by definition 1 d bar t, 1 will go to 1. 1 is a constant function 1, which will go to 1. Okay. Now you apply this on t star t 1 d bar t xx. I mean, this is what it means positivity means. Positivity S and T, if you have two operators, S is greater than T. If S minus T is positive. S minus T is positive means SXX is greater than TXX. That's what positivity means as the definition of positivity. So this is less than or equal to now XX, XX, identity XX. Okay, so this is equal to norm X square. Now if we have assumed that X belongs to the range, okay, so you can take this, I mean, on 1 d bar, all spectral projection commutes with T and T star. It's all in the same L infinity. I mean, okay, this is in the same L infinity, so they will commute. I mean, it's like L infinity. It's like a range of L infinity, so it will all commute. So 1 d bar, you can take it here and put a 1 d bar here, and you don't need 1 d bar. This just says that T star T, I mean, you can take the T star there. This is just Tx square is less than or equal to norm. Okay, this is for, but then T, so but then T leaves is, I mean, T commutes with 1 d bar, so it leaves this projection, the range of this projection invariant. So this implies T square x is equal to T of Tx, but Tx is again in the range of 1 d bar. Okay, because it leaves it invariant. So you can apply the whole same thing. So it will become norm t square power. I mean, this is again less than or equal to norm x square. This is less than or norm tx square, which is less than norm square. So we have this t power n x power is less than or equal to norm x for all n. So 2 to 3 is trivial. Okay, so let us prove 3 implies 1. So we are going to do the same thing what we have done for self-adjoint operator, but bit more complicated here. I mean, slightly we have to change this. So what we want to do? We assume t power n x is bounded. in n is bounded. This set is bounded. So then we want to prove that x is in the range of the spectral projections corresponding to d bar, the unit disk. Okay. So let um equal to mod all z mod z is greater than 1 plus 1 by m. Okay. Then um decreases to d bar. Right? Decreases to d bar. Now we want to prove that, so this implies 1 as functions, 1 converges to 1 d bar. Okay. So this implies 1 t will converge strongly to 1 d bar t between. So you can instruct 1 t x will converge to 1 d bar t x. Okay. We want to prove x is in the range of this spectral projection 1 d bar. So we want to prove 1.
Like in the definition of it should be less than mod z less than 1 plus 1 by n, right?
In the definition of what? Mod is it?
Less than 1 plus 1 by n.
No, it should be greater than, sorry, so complement. Right? Oh, you are right. That's true. It is less than that. Correct. Less than, and if you take the intersection, then why are we consider the okay, let's see. You are right. Should I consider that's right. So we have so that's right. So we want to prove that 1 x converges to this. That's right. So we want to prove this xm equal to So we want to prove, okay, that's okay. 1 umt of x converges to 1 d bar t. Okay, where is the, this is fine. This is fine, no? If I take less than, I can take, I use unnecessarily this bar, that's not needed. I used it's fine. I mean, that's for open set, but I'm using it for closed set. Maybe call it EM. It should be close to 1. We had a lemma earlier, so maybe I should just take, I mean, from I call it itself. I take the open side. Then clearly this thing certainly true. Okay. Okay. To prove 1 d bar tx equal to x itself, enough to prove 1 of tx equal to x for all for all n. Okay. So that is 1 complement of tx equals 0. That's what we want to prove. Right? Okay, so that's what we want. So let xn equal to 1 um complement of tx. Okay. Notice what? Okay. So we did something for self-adjoint operator. We want to use that self-adjoint trick itself. We want to use that. Okay. So let us try this. So we know this sequence is bounded t2 power n x, okay, which is actually equal to t power n star t power n x. Okay. So this is a self-adjoint operator, which is actually equal to t star t power n x. Okay. This is a self-adjoint operator, right? Now this is actually, so this is a self-adjoint operator. Now you can insert any projection inside this. The norm will only increase, and norm will only decrease. I want to, so t star t I want to insert. So I want to take one of this set, x in real number, because I'm taking self-adjoint, x in real number, mod x is greater than, so 1 plus 1 by n. This is open, greater than or equal to 1 plus 1 by n. Okay. So I have taken this set, then I am taking t star t. I'm inserting some projection here. Okay. Then times t star t x. Okay, I can do this. But then this is t star t, and this is a spectral projection of t star t. So you can commute with that. You can take it that side. Okay. So this implies, so this is t star t power n, of course, t star t power n times 1 of whatever that set times t star t acting on x. Okay. Okay. Why did I write like this? Because we had a lemma, if you remember. I mean, if you have one of this set, x greater than or equal to some epsilon of t non tx is greater than or equal to epsilon times non x square. We proved a lemma with some properties. This is for self-adjoint operators, for t self-adjoint. Okay? So here I'm going to apply for this t star t self-adjoint operator. Right? Okay. So I'm just going to apply that. I mean, see, we had this earlier lemma for any self-adjoint x. Self-adjoint x, this is true. One of this set, t greater than or equal to epsilon, okay, of this x acting on any x. This greater than or equal to epsilon times non x square. Or even not that. This is the, and what I said is true, but I think the statement we proved is in this form. Xx is greater than this for all x in this range of this projection. One of it's the same thing in writing. This is true for all x in one of this interval, epsilon to infinity. Okay, fine. So I am just going to use that. I have t star t power n, then I have this. But then notice that this projection, one t star t of this whatever that set, mod x greater than or equal to 1 plus 1 by n, is precisely equal to 1t of this projection z such that mod z is greater than or equal to 1 plus 1 by n. This is the same lemma. Maybe I will give it as an exercise again. So this is a, you have written that assignment. No, I haven't checked your assignment. You have this 1t of any set E is same as 1 f of t of f of e. Proved this in the assignment. Has everybody got it? Or I mean, if somebody gets it, it's fine because you can discuss for assignment. Okay, we don't need to discuss it. Okay? I'm sure you are discussing, so you can discuss. So this has been proved.
Sir.
Yeah.
Sir, this was given after the midsum portions, right? So we didn't attempt this question.
Oh, okay.
Can we submit this after?
This assumption is in pending. Okay. Oh, this was in spectral projection, right?
So can we submit this on the for the ensem assignment?
Okay, okay. So you can include that. Then you prove it for normal itself. Okay. Now we have proved Fugledes theorem for normal operators. So assignment, prove it for normal. Okay. Directly prove it for normal. You don't need to prove for normal.
Okay, sir. So that question will prove it for normal operators.
Normal operators. Okay. So this is another assignment. So once you know this, this is just clear. Okay. From this, it's clear. You are just taking the mod function and then mod is a continuous function. So from that it follows. Okay. Okay. So this is true. Okay. The earlier lemma for because of that this is true. Okay. So where were we? So we have got this inequality and that is greater than or equal to. So we have, so this epsilon here is 1 plus 1 by n. Okay. So here in this line, you have this 1 t star tx, which is in the range of 1 t star t, which is same as 1 whatever that disk, the complement of the disk, spectral projection corresponding to the complement of this disk. I am applying 1 t star t here and then getting this 1 plus 1 by m. I mean, this epsilon times norm x, which is 1 plus 1 by m times norm of this. But then there is another t star. I mean, this t star t takes any element. I mean, leaves this projection invariant. Okay. So what I'm saying is, you can go on taking this by induction. This is just equal to 1 plus 1 by m. So we have to use the t star t power n. So which is I should get 2m somehow. This is greater than or equal to norm xm. You will get xm first. So when you apply this 1e, when you apply the spectral projection, that is what is xm. I have called it as xm. Okay, I have called it here. Okay, so we get we get xm. Then after that, you are going to get this power. I mean this epsilon, which you will going to get 2n times. Why do you get 2n times? That's because so, no, this is 1 plus m square. No, that's right. This is mod z greater than 1 plus m. There is square somewhere. No? This is mod z is greater than this. This is sorry. This is because you are taking here. So mod z. This is the function is t star t. So this has to be square here. Okay? Right? Not here. Sorry. Mod z greater than 1 plus 1. Here I am taking t star t. So here it has to be square. Because the function f, I mean this assignment problem, where you are applying for the function f equal to mod z square, which is t star t. T star t corresponds to the function z bar z, which is mod z square. So this has to satisfy mod z greater than this. So that is why you get this 2 power m here. Okay. You will get 1 plus 1 by m square in each step whenever you apply t star t. That. Okay. Here also it's square. Here also it's square. Sorry. This is confusing.
So
No,
like can you scroll bit up?
up. Yeah.
Uh-huh.
We have
That's
taken
so,
t 2 power n x, which you have written as t star t n. Then we have just
that's so
inserted a projection. Okay,
like
once you
it should be
insert
2
a
power n.
projection, that projection is same as this mod x greater than this is same as mod z greater than that. I mean, when you apply the projection for t, okay, that is mod z greater than that 1 plus 1 by m. But here you are applying the projection for t star t, so the mod x should be greater than, I mean, x is greater than z. T star t is positive, no, so you don't need mod x. So
Sir, I mean like you have written t star t power n applied to x, right?
t star t power applied to x, correct?
It should be 2 power n minus 1, right?
2 power
N minus 1.
y n minus 1.
Because you have taken t power 2 power n x.
T 2 power n I have taken. Here t star t power n I have. Okay, 1 t star t will come here. This is the projection. This whole thing is a projection. Okay, this whole thing is a projection. Okay? So that I am bringing it to the x, and I am applying the earlier lemma, whatever I have written here, this epsilon lemma for this member, this x multiplied by this spectral projection. For that I am applying. So each step I will get 1 plus 1 by, the epsilon is 1 plus 1 by m whole square, which I will get each step. Okay, so I will get 1 plus 1 by m, and I am applying n times t star t. Okay, so I will get 1 plus 1 by m power 2 power m. Okay, that's what I will do.
No, I mean like t power 2 power n x. Like you have written it as t star
Oh,
t
2
power
power,
n
t
applied to
power,
x.
t power, t power, t, that's right, no? T star t,
Power 2 power n minus 1, right?
t power 2 power n minus 1. Why, where are we getting minus 1? T power 2 power n I have.
Yeah.
I am
You have
having,
written it as t star t power n x.
correct.
But it should be instead of n, it should be 2 power n minus 1.
No, why? T, I am applying the C star identity here, okay, which we have done earlier, so I didn't explain much. I'm applying this. Norm T star T equal to norm T square. Okay, that's what I'm using. Is that what I'm using?
Sir, what he's saying is t power 2 and
Because I'm
norm of
sorry,
t
sorry,
power
I'm
2
not
and
using this. That's not what I'm doing. T power 2n now. So it's oh sorry, it should be just 2n, right? Yeah.
so
It
yeah,
is,
that's
sorry, I had different thing in mind. Sorry. It is just 2n. It is just 2n, which is just same as tnx, and then it's okay.
yes.
It's using this tx equal to t star t x, which is equal to t star t. I mean, if you want, if you don't mind, half x, t star t half x. Okay. So if you have 2 power n, it will be, or if you have t square, if you wish, for example, you can take it. It's okay. When you just verify. It's okay, no? Maybe I will write it again.
So we're just using the C star identity, right?
No, not C star identity. C star identity will get 2 power n will come. I'm just saying we are using this t power 2n x. Okay, this is equal to t power nx. Yeah, you can take t power n star x, which is equal to, you can bring it here. I mean, no, t power nx. We are considering the norm. I'm sorry. Just write it here. We are considering t power 2n x. Okay. T power 2n x, which is equal to t power 2n x, t power 2n x, which is equal to t power 2n star, t power 2n x. Okay. Now you can write this as T star T because it's normal. You can write it as T star T whole power 2n, yeah, 2n x, which is equal to T star T power n x, T star T power n x, right? Which is equal to norm T star T power n x, right? Okay, this is what I used there. Okay, now it's fine. This is not 2 power n, it's 2n, and we get it's not 6 or anything. Fine.
Yes, sir.
This is what I used. Okay, I'm actually taking a square root kind of thing. That's what I said earlier. I mean, I want to do it for one and then kind of induction, but directly it follows. Okay, this is what I used. Okay. Okay, so from here, so finally we got that. What do we get? We initially started with this, and then we got that this is greater than something. So this becomes unbounded. Okay, this implies T power 2n x is unbounded if xm is not equal to 0. So xm equals 0. That's what we wanted to do. Xm equal to 0 is what we wanted. Okay. Xm is the projection on this one complement T acting on X. This projection acting on X. And that Xm we want to prove it's equal to 0. That's what we do. Okay. So the lemma is 4. Lemma is 4. Okay. Lemma 2. Okay. So next, what do you want to do? So now coming back to continuation. Proof of the theorem. Okay, so what do you want to prove? So we started with the theorem. The theorem is T is a normal operator and S is any operator, anything in P of H which commutes with T, then it commutes with F. I mean, commutes with F of T for all F in L infinity. So we notice that it is enough to prove S commutes with all spectral projections. It's enough to prove that. Okay, so we have just proved. So we have just found a criterion for the. So first thing is, so let script F equal to all E in the Borel sigma algebra of C. Okay. So a projection commutes with T if and only if it is the range is left invariant by the T. Okay. That is clear to you, all of you. I hope you know. I mean, if you have TP, you can actually. I mean, this I said earlier. I believe. If you have any projection P, then you can write with respect to that projection, you can write that HS, H naught, direct sum, H naught curve. Okay. Then you can write any operator as a matrix. And you can write that projection as 1, 0. Okay. Then you just matrix multiply, and then use the commutative relation. I mean, it's a commuting relation. Then you get that T2 and T3 will be 0 because of that. So that will mean it's just T1 and T4, which means it will leave this projection invariant. And if it leaves invariant, then it certainly commutes. It leaves invariant means what? It leaves the projection invariant, and it's not reducing, it's invariant, and its complement also invariant. Okay. Then it has to look like this. It has to look like a diagonal operator, so it will commute. Okay. This exercise you should do. I'm not giving it as an assignment, but you should do this exercise. Okay. So to prove that something commutes with the spectral projection, that's what we want to prove. We prove that it leaves invariant, such that S leaves, S is the new operator, S leaves 1 E T invariant, range of 1 E T invariant. Either range or projection invariant means is the same as that. Okay? It commutes to the projection, it's equivalent to saying it leaves the range of the projection invariant. Okay. Now first claim 1. D bar is in script F. Okay. That is because if X is in 1 d bar. X is a normal operator. So I'm wondering about the orthogonal complement. One X is in one d bar, X is in the range of one d bar. So this is equivalent to saying t power n x is bounded with the earlier lemma. Okay. This will imply S t power n because it's S is a bounded operator. This is bounded, but S commutes with this, so this implies t power n Sx is bounded. But then this will imply Sx is also in one d bar. Okay, the range of this. So what about the orthogonal complement? I'm not sure about this. So if this is true, why is it true for the orthogonal complement? D of x is there, then it is true. Something commutes if and only if it leaves the subspace and its complement in area. No, otherwise it can look like this. Right? It can look like a T and then it can have the other operators here. Okay, that will not commute. Okay, let's see if the last time also I didn't worry about this, is it? So if x is in the 1 d bar complement of t, okay, then I think it's not worried in the book also. It's not clear to me. Is that clear to anyone? Anyone of you? Why does it leave the orthogonal complement in area? This lemma says that it leaves the projection, range of the projection. I mean, it leaves it takes the projection, range of the projection into itself. But why should it leave the orthogonal complement also in area? Something commutes with the projection if and only if it leaves both P and orthogonal complement. No. Have an operator T. If it takes Tx into T of x not equal to 0. That just means it will look like some T1 and it will not take anything from, so it can have some T2 here and it will not take anything. So it will not take anything from the first Hilbert space to second Hilbert space, the orthogonal complement. It will look like this. But then this will not commute with that. So you have to prove that it commutes with the orthogonal complement also. See, earlier theorem also we didn't worry about the orthogonal complement. Orthogonal complement corresponds to the set complement of D bar. I mean, it's precisely you take D bar and you take its complement, and the spectral projection corresponding to that is that. So we have to prove that that spectral projection is left in there. Is that true? Because we don't know anything about S star. Okay, that's what we want to prove. It's only S commutes with T. S star need not commute with T. That's what we want to prove. We in fact want to prove that S star, I mean, S commutes with T, we want to prove S commutes with T star also. That means S star commutes with T. That's what we want to prove. So this point I have to, I'll think about it. It's not clear to me. Or if it is clear to you, you tell me. Okay. So this invariant about orthogonal complement, we must worry. I don't think it's the point is considered in the book. I think it's only this. So if X is in that projection, then Tx is also there. But we want to prove that it commutes with T. To commute with T means okay. We don't have to worry about this. We change that. Let us just change this. I mean, a projection commutes with an operator commutes with the projection if and only if it leaves the range of the projection and the range of the orthogonal complement invariant. Okay, range of the projection into itself and the orthogonal complement. It has to be diagonal with respect to that projection. Okay, here I am just saying that you take all those E such that S in the range of 1E is contained in range of 1ET itself. I am just considering those sets which leaves the spectral projection invariant. But then I will prove this contains all BC, all sets in the Borel sigma algebra. Then E is there, its complement is also there. Okay, we will get it somehow. But what we will do for the complement, we have to think about. Okay. So this implies D bar is there. Okay, that is claim 1. In the claim 2, so any D is there. Let D Z R equal to all those Z naught R, all those Z such that Z minus Z naught is the disk around Z naught is less than 1. Okay. Then D bar of ZR is in BC. That is just clear. Proof. Apply this to, I mean, I have given you the exercise. Apply to, if S commutes with T, it will commute with T minus Z naught divided by R. Okay, R is greater. Okay. It will commute with that. So because of that, it leaves, then it leaves that the corresponding projection. Apply this to T minus Z naught. Okay. So that's why it's true. This is clear now. So then we want to prove that it's a sigma algebra. We want to prove that script F, it contains all an algebra of, we want to prove that algebra of this kind of set, AP cross CD, this kind of things. Okay, in the complex plane, these kind of things. This is complex plane identified with R2. So this kind of things. Then we want to prove this is an algebra. disjoint union of such things is an algebra, then you prove that it's a monotone class, and that's what you. So we have to go through a long journey. We want to check one by one. Okay. So we have proved that any such disk is there. Okay. So the next thing is, next claim is, so we have proved any closed disk is there. So then any open disk is also there. No, we want to prove that it's closed under monotone limits. Then we want to prove open disk is also there. Okay. Then this script F is closed under increasing union and decreasing intersections. Okay. That is just clear. If En increases to E, okay, then one En will converge to one E. Okay. Now, so one E will converge to this. In particular, this projection 1 En of T will increase as a projection, increase to 1 E. Is that clear? If you take, this, see, if you have two projections, P and Q, okay, and a projection Q is contained in P if and only if P minus Q as an operator greater than or equal to 0. This is projection. These are all the 1E. En increases to this. So 1E minus, in particular, if you can even see that 1 EM minus 1 En as functions is greater than or equal to 0. Okay. This implies 1 EM T minus 1 En of T is greater than or equal to 0 as operators, which we are, because positivity is preserved under the homomorphism because of that. Okay. But then this precisely means that this range of 1 En T is contained in 1 En T because they are projections. Okay. If you have two projection, because if P is, leave it to you. This is easy exercise. Okay. If you have two projection, then Pxx is norm Px square. Norm P. This just says that P minus Q times X is great. P minus Q is a projection, and it's also greater than or equal to 0, means one is contained in that. Okay. So you are using all the properties of this indicator function. This is contained in that. Okay. And then this and 1 EM will converge to this, means 1 EM. So now 1 En as function converges to 1E as function, implies that 1 En T as functions, okay, as functions, converge to 1E strongly. Okay. The strong convergence of projection is just means that it is the increasing union. Okay, this implies. Please verify. These are all some exercises in projection. You can verify that union of this range of 1 En T equal to its closure is equal to range of 1 Et. Okay. We actually did this for some, you took some finite rank projections, and it converges to identity strongly. That for any, we have finite rank projection converging to identity we prove, and there we use similar thing. Okay. Because you can take, so it's very similar to that. If some sequence of projection increase, some sequence of subspaces increases to some subspace, then the corresponding projection will converge to that strongly. The conversion should be strong. Projections will never converge unless some trivial situation. Projection will never converge to in norm. Okay. So it will converge in strongly. Okay. So this you get convinced yourself. Okay. If you don't get convinced, you ask me. We can prove it. You can write down the whole thing by, with the definition, and you can prove it. Okay? Oops. So that is true. So because of this, it leaves each one of them. I mean, if you in the union, it leaves each one of them. This implies that each of this en, each of the projection one en t. It leaves, suppose this t s leaves one en t invariant for each n, then it should leave one et also. So this implies e is in that script f, whatever the script. Okay, this is fine. Okay, so now claim 4. All open disks. We have proved that closed disks are there, so open disks are contained in this. But that because any open disk can be written as increasing union, or and decreasing thing also. Decreasing intersection of we just saw that. Okay, this decreasing intersection of. This is true for open thing. The same proof you can write it for decreasing intersection also. The same thing is true. Okay. The sets will converge, so the corresponding indicator function will converge. So because of that, the projection will converge strongly, and for decreasing thing, that's what it means. Okay, the intersection is that. The union will be changed into intersection. Okay, it's the same thing. So open disks are contained in that. Okay, so that is one thing. So then the next thing is claim 5. Half planes are there. Okay. So what are the half planes? Half planes are, you can take upper half plane or right half plane, left half plane, lower half plane or something. All these half planes are there. It is enough to prove one of them. The proof will be similar for all these things. Okay. Once you have the disk. For example, you take the right half plane. Right, this is right, no? So right half plane is RA, which is equal to mod Z greater than E. Greater than A or greater than A could be greater than E. Okay. Now this is precisely equal to, so what is this? No, not mod Z. Mod Z greater than A is outside of the circle. I'm sorry. Real of Z. Real of Z is greater than A. This is just you have this A point A here in the real number where A is in real. Okay. So you have this real. This plane is this. Right of plane is this. Okay. Real is greater than this. Okay. Now this you can write it as you take some point. You have here, you take A plus N. Okay. Then if you take the circle with radius N, it will hit here. It will have this. But then it will cover all the point when N is increasing. So RA is equal to union of all those disks. There's possibly open disk or possibly closed disk. Okay, D bar. But that will include A, no? So you take the open disk. D bar of the center is A plus N, radius is N, not A plus N, A plus, yeah. Correct, A plus N. This is equal to union of all those Z such that mod Z minus A plus N is less than N. Less than or equal to N means it will include A, no? So you want it strictly greater than that. So this is increasing union. So this is right, no?
Yes, sir. Yes, sir.
So okay.
The union is over all n, right?
Yeah, union is all n, correct.
This is correct.
Okay. No, I am wondering whether to take closed or open. Okay, so we should take the Z minus A plus N. This is less than. You take this circle, and eventually it will cover all the points here. Okay, so this is the right answer. So because we have already proved increasing union is there, this implies that RA is in script F. And similarly, you can talk about LA, which is the left, and you can take the upper half plane, which is the upper. This is the left half plane. I don't want to write all the it's in the book. You can read. Okay, upper UB or lower, upper lower also. LB, they are all in the script F. You have to, instead of real, you have to use imaginary for U and L. Okay, and here you have to take it on the other side, less than that. Here it is greater than the upper half plane, and you can include that A also. Okay, that is just you can take the opposite. You can, I mean, again, because of the increasing union and all those things. So because of that, it's closed off plane, open off plane, closed off plane. Everything is also there. Okay, so final claim. I don't want to go through each and everything. It just follows from that. Oops. Okay, then script F is closed under finite intersection and countable disjoint union. Okay, proof. If you take E1 up to En in the script F, you want to prove their intersection is also there. Okay, but then what is the intersection? So now we want one of the intersection En. Okay, n equal to k equal to 1. Ek. This is just the product, right? Right? If we take indicator function, then their intersection is just the indicator function of the intersection is the product. Now you apply the homomorphism, then this one intersection k equal to 1 n ek, this t will be just the product. Again, this is here the product of the projections. Okay, 1 ek t. Right? You are applying the homomorphism. Right? Okay. Now this implies, but then here it's a product of the homomorphism. Now this implies, so there you take the range of these two projections are equal. I mean, so these are all commuting projection. If you take some finite family of projection, if they are commuting, then the product is also a projection. If and only if they are commuting. Okay, if you take two projection, then the product is a projection if and only if they commute. If they don't commute, then it's not, the product is not a projection. Again, also, if you take two projection, their sum is a projection if and only if they are orthogonal with respect to each other. There should be some disjoint. I mean, disjoint as projections. Okay, the range of one projection is contained in the orthogonal complement of the other projection. Okay.
Yes, sir.
Seen these things. I mean, I could have given all. Maybe I will give the exercise. Okay, assignment. What are all the assignments? So these two things I want. Here, I mean, that matrix product I don't want to do. Okay, I mean, I don't want to give it as an assignment. Some projection that also you can do. You try to do it as an exercise, but let us do this. So P1 up to Pn projections. Okay, this is assignment. So do it as an assignment. So in the review of my course, someone complained that I give assignment within lines or something. Unfortunately, I cannot avoid. And another thing is, it's good. That's what that should ensure that you follow the course. Okay, I mean, so if I give it as a list, then you may not read these things or you may not be attentive. So it's better I give it like this. So if you have P1 up to Pn projection, then the product P1 up to Pn is a projection if and only if P1 up to Pn mutually commute. All of them commute with each other. Okay? That is one thing. And P1 plus up to Pn is a projection, which is equivalent to saying Pi, the range of Pi is contained in range of Pj, Pj perp, range of perp, like the perp outside, for all I not equal to j. Okay? They have to be mutually orthogonal. Then only that will happen. Okay? So they should be mutually orthogonal for each I and j. Okay? So these things we should have done earlier in the earlier course, but it's okay. We are studying more projections here, so this is true. This projection are like sets. Okay, commuting projections are like sets. Commuting projection precisely behave like sets. I mean, you have the distributive law, all those things for that. But when they don't commute, you will not have distributive law and other things. That is what is called the quantum logic. See, if you talk about logic, I mean, logic can be stated in terms of projection. Sets. Mathematical logic is in terms of sets. If you take, I mean, the AND statement is the intersection of sets, OR statement is the union of set, and you must be knowing this idea. But then when you want to get to the quantum logic, okay, there you want to take intersection, that is the intersection of projection. When you want to take the OR statement in a quantum thing, you have to take the projection space generated by those two projections. If they are commuting, they behave precisely like sets. But then if they don't commute, then the distributive law is not true anymore. So in quantum logic, distributive law is not true, whatever it means when you want to talk about distributive law. That's because these projections, I mean, I will, if you do my next course in quantum computation, I will explain these things, okay? You can read it otherwise.
So this is like
Yeah.
bit like Boolean logic.
Yes, yeah, exactly. You said Boolean something, no?
Yeah, Boolean logic.
Correct. Yeah.
And operator or operator.
Correct. Yeah. I'm just saying distributive law will not be true, but if they are commuting, then this you can do all that. Some will correspond to the corresponding. Okay. So why did I do all these things? So because of these things. So and if you take and the product of this projection is precisely the intersection of this projection. This is equal to this is just the intersection of this projection. Range of the product of this projection, I equal to 1 to k equal to 1 to n, 1 ek. If you take product of projections, then the range of the product is the intersection of all the projections. Okay, intersection range of 1 ek. So all I am saying is range of 1 of intersection ek for finitely many. Okay, k equal to 1 is same as intersection of k equal to. Here I am taking the intersection with projections, okay, rather than sets. The property of the sets is precisely preserved under when you take the corresponding projection. Okay, but this is true only for commuting projection because they are commuting. The the statement about the set is translated to the projection, okay, because they are commuting. Otherwise, it's not true. So because of this, it's closed under finite projections, finite intersection. Okay. And similarly, I have so this sum you can take it to be infinitely many also, but then you have to use the strong convergence. Okay, there's a sum of, if you take sum of mutually orthogonal infinite sum, countable. I mean, it should be countable. So if you take a countable, or you can consider net, but we are considering separable Hilbert space, so you will not have uncountably many mutually orthogonal projections. So if you take countable set of mutually orthogonal projection, then the sum is a projection if and only if, I mean, sum is a projection, and the sum is a projection if and only if they are mutually orthogonal. And the sum is taken in strong topology. Okay. And the same statement will imply that. So similarly, if you take P1 up to P1, see if you take a Pn, I'm not talking about Pn, En. Similarly, if En contained in F and En intersection Em is empty, okay, then one En, the corresponding sets, okay, one En T intersection one Em T is empty, not intersection. They are in the orthogonal conjugate. Sorry. I mean, that's what I meant, but this implies one En T, one Em T equals 0 if not n not equal to n. So this implies 1 EMT, the range of this is contained in range of 1 EMT per. Okay. So if they are disjoint, I mean, if the En is a disjoint family, that means 1 ENT is a mutually orthogonal family. Is a mutually orthogonal time. Oh, a past family of projections. I'm sorry. I didn't look at the time. Family of projections. My handwriting is becoming very worse. Okay. So then you just verify this. Okay. One of this is nothing but the sum of this. Sum of 1 EN. Okay. And that is equal to, I mean, so this implies as functions. Okay. Then the range of 1 EN T is nothing but, it is actually direct sum, but you can, it is a direct sum. It's not union. The sum is the direct sum. I mean, if you have two projection which are orthogonal to each other, then P1 plus P2 is the orthogonal direct sum of those two ranges. But something leaves each of the subspace invariant, it will leave the orthogonal direct sum also invariant. Okay, so this implies so please go through this and we'll discuss. If you have any problem, any doubt, we will discuss it. Okay, because it has many questions which we haven't dealt with, projection and all those things I'm saying. I think you have to do this exercise, simple exercise, whatever I said. Considering orthogonal projection, product of projection, intersection, the range generated by that, all those things. So once it's day after tomorrow, we will discuss and do the remaining. Is that fine?
Okay, sir. Yes, sir.
Okay, I will end.